Hello everyone, welcome once again to my YouTube channel. Today we'll be looking at the other libraries in the scikit-learn library. In our last video we looked at the train test split function in our scikit-learn library for machine learning. So this video we'll look at the other libraries. Stay tuned.
The next function is standard scalar. Now, when you are dealing with machine learning problem, it's just that this is a data set, synthetic data set, so it's kind of like almost perfect. If it was a real world problem, it's not that perfect. You understand? So what this standard scalar does, it rescales your data. If you're working with a regression problem, let's use regression problem now. For a regression, for you to do regression, for you to use a regression formula on any problem, number one, that problem must be normally distributed. Now, normally distributed. Now, what do I mean by normally distributed? Let me give a practical example. The data set has to look like this. I want to be sure I've dropped this thing. Okay, anyway, the data set should look like this. So now, if the data set looks like this, what does it mean? It means there is where it started from. It went up and got to the peak, and then it came down. So, for example, now, if they open let's say, a pack for the first time, because it is a new pack now, so many people will rush. Hey, they want to see what is happening. They want to see what is happening. People will be coming. So the first person comes. So that person is 1, 2. The number of visitors are increasing. They're increasing. It will get to a peak. That, wow, this is the peak of the visitors. For example, now, the pack is complaining, hey, they had an 80% increase. That is totaling 3 packs. Now, that was 80%. They got the 80% from 3 packs. There was a sudden increase. Well, it could be because there was an advertisement or a new pack feature. So many reasons. So everybody came. There was this craze. Everybody were rushing. Let's come and see it. For your information, next year, if they did not do advertisement and they did not add a new pack feature, the number of people that will come will not be as many as the ones that came last year, because some will be like, okay, we've seen the new pack feature now. What is there? Some will like it, some will not like it. So next year, the number of people that will come will not be that same 2,000. Maybe it will reduce to like 1/8 here. If the pack doesn't do adverts, it doesn't refurbish its pack and make things better, it will continue to go down. They go down until it gets to 0.0 and you hear, they've shut down business. So yes, in everything, people, there's this craze of, it's a new thing. But after some time, that craze will die down. So that's a normally distributed data. So the meaning of this is, if you plot this data now, X, if you want to plot a graph, this is a graph like this now. This is a graph. I'm trying to draw a straight line here. So this is your X-axis, and this is your Y-axis. Don't forget, we divided our data set into X and Y. So if you plot it against Y, it should produce something like this. It should produce this curve. These are some of the things that your data set must fulfill for you to say, okay, now I should use a regression model. Don't forget, machine learning model is designed with that regression formula. So when we are using linear regression, it has its formula, that regression, normal statistic regression formula. That is what is programmed into it. Okay, so what standard scalar does is, in case your data set is not normally distributed, what is it going to do? Sometimes now, that is why there's something called exploratory data analysis. At this point, you are checking your data using charts. You are checking your data using charts. So, for example, if you say you want to check for skewedness, that is SKEW, skewed. Is it skewed to the right? For example, this is your chart. If you plot your data set, if it is right skewed, your data set will look like this. It will be a bar chart. All these things is a bar chart like this. So it's a bar chart. So your data set will just bend like this. This is not normally distributed. It is supposed to look like this when you plot it. But now it's bended to one corner. So that is what standard scalar does. It will make sure it will now work on the data so that the data will now follow the normal distribution. Linear regression. That is the model we are using. SVR. That is another model. Now, what is SVR? SVR is under SVM. What is SVM? Support vector machine. Support vector machine. Now, in machine learning, we have several models. Several models. For the classification, we have K nearest neighbor. I don't want to just bug you with mentioning all their names. It's easy to get that one. Okay, so for you to do a machine learning task, it is advisable to use minimum of 2 models. Why? At least one of the model will perform better than the other. Now, machine learning is not that difficult. What makes it stressful is in working on your parameters, that is your models, to make sure they predict as accurately as possible. Linear regression model has its pros and cons. SVR has its pros and cons. Decision tree model has its pros and cons. Okay, for example, if we decide to use decision tree, well, that is majorly used for classification model. Why for regression, for linear? For regression, we can use logistic regression. That is the classification aspect of regression. If you want to do classification problem, but that one is only yes or no. Anyway, let me not bug you with that. Okay, so now, decision tree, if you have to use decision tree, you can't use decision tree model on a large data set. There's going to be an issue. It will be too slow. Now, random forest model, don't stress yourself with their names. Once you browse online and say, what are the machine learning models? You will see all these names and you will remember. So random forest model is an improvement on decision tree model. You understand? XGBOOST. Hey, the meaning is extreme. The X is extreme. The G is gradient. Then the boost, boosting. Extreme gradient boosting machine model. This one is the advantage of this one. It can learn and learn very well. It will learn. At least all those information you gave it to it, it will, if you give it that same information in future, it will easily tell you this is a dog, this is a cat, this is a this. Or it will easily tell you by 2026, you are going to get 10,000 visitors. It will easily tell you. But there's a problem. Now, what I just said now, the machine learning term, the machine learning word for that is overfitting. Overfitting. Fitting is F-I-T-T-I-N-G. Overfitting. That is, he has learned so well that it will have problem in future when you bring an information that he has not learned before. You know, in this world, you cannot know everything. What does that mean? Don't assume you've seen all the animals in the world, though. There's an animal. Okay, for example now, do you know that some cats or a cat can cry like a baby? I don't know if you've heard a cat cry like a baby before. You would think it's a baby that is crying from far. Now imagine such situation. The mother was trained with meow, meow, meow. Only for we, the human being, to go and gather data. And we gathered a data of a cat crying like a baby. If you feed that information to XGBOOST will categorize that cry as a baby. Meanwhile, was it a baby cry? No, it was a cat cry. So it learns, but if you give it meow, it will quickly tell you it is cat. He overknow that one. Overfitting, I too know. But oh yeah, tell us future problems. That is, we bring in a new feature. Let us bring it down to this our task. We're dealing with park visitors. Okay. I think we have, how many columns we have, Seth? I don't know. Let me assume we have 15 columns. One of the column is the one that stands for the target column, which is the total number of visitors. Every other column is there. In feature now, if we decide to add another column, for example, is there an event around the park? We'll put yes or no, because if there's an event around the park, sometimes, let's say there's a wedding happening around the park, some people can just decide to stroll into the park and say, oh, let's even see what is happening in this park. Yes. So that is a new feature we are adding to this model now. If we add that new feature to the model now, the model can be a little bit confused and there will be error. So one thing about XGBoost is it knows how to learn very well, but there can be challenge with future learning, that is problem. So there are parameters you need to work on to make it not to overfit. This XGBoost is a little bit complex, but not that complex. So, but let's just leave that one at the corner first. Let's work on linear regression and SVR. Why did I move to this XGBoost? I was trying to explain the reason why we use more than one model when doing your machine learning, to increase your accuracy, so that the cons of one model, the disadvantage of one model will be mitigated by the advantage of another model. When you do many, at least you will pick the one with the best score. So now, these are the two models we're working with, SVM and linear regression. So SVR means support vector regression. We also have the support vector classification of it. So many of these models we have, they have the regression aspect and the classification aspect. So just know that one. But the one that doesn't have the regression aspect is k-nearest neighbor. K-nearest neighbor doesn't have the regression aspect. It's strictly a classification model. So that's for that one. All right. So now we're looking at the metrics. Now, what is metrics? How to measure. We already ahead now, measuring things now in Power BI, the metrics or whatever. So you're just trying to measure something. So what are we measuring here? We're measuring the accuracy of our model. The accuracy, how accurate is this model? We're trying to check, okay, after the model predicted, how close is the result to the real life problem? How close is the result to the real life problem? So let me scroll there to where we ran it so that you can understand better. Okay, so here it is. Mean square error. Mean squared error. First and foremost, before I explain, when you are dealing with regression problem, you have to use mean squared error and R2 error to check your accuracy. Those are the most common metrics to measure your accuracy. But if you are dealing with a classification problem, you will need accuracy score, F1 score, and so on. So the measurement of the accuracy of your model, the metrics to use depends on the model you are using. Okay, so now let's look at how it worked. It's mean squared error. what you are really looking for is the root mean square error. The R there is root. Root means square error. And to find root, you just say square root. Square root the result of your mean squared error. That is all. To get your RMSE. That is root mean square error. Okay. So don't forget, what you are trying to check now is you are trying to compare the predicted outcome of that your model that you trained. Don't forget, you splitted your model here. We splitted the model to train and test. Why? You train the model with 80% of your data, and you are going to test it with 20%. So look at it here now. Look at the mean squared error. Look at the parameter passed into it, into the function. The parameter we're passing into the function now is your y test and your y predict. Look at it here. Y test. Don't forget what I said the test is. The test is your 20% that you kept at the corner to use to check the accuracy of your model. So follow me closely, please. I need to be very, very patient here. Okay, so this y predicts here. This y predicts here. Look at it here. This is it here. This is y predicts. This is y predicts. Okay. So what is this line of code doing? Models. What are our models? Look at our models here. I told you we're working with two models, linear regression and SVR. So this is the SVR model, and there's a linear regression model. So I believe you know this one for I in range 2. Models now. So we pick the first model, which is linear regression. We fit it to the trained data set. That is the 80% of the data set for the X and the Y. We train it. So you are telling the data set, okay, these are the information on my table. The whole table now, 80% of the whole table, that is the X and the Y information, pack everything into the data set. So what the data set will do is saying, okay, if you have this level of advertisement, if you have holiday, if you have this, if you have all this level of information, these are the number of visitors you will be having. So all those information, we are packing everything into the model and we're training it with it. So anytime you see these features, these are the total numbers of visitors you should expect. Nice one. He has learned to. So that is what this line of code does. You are training it. Now, this line of code, Y predicts, what it does now, it will now predict a Y. Okay. We've trained our model. Are you with me? We've trained the model. Now, we want to see whether our model has learned to. So what we are going to do now, remember, we split our data set into two. 80% has been given to the model to learn. There is 20%. Don't forget that 20% of the data set still contains X and Y. So now, the function of the X there, that 20% of the X test, we're going to pass it into the model now. So what you're trying to tell the model is, okay, you know, we did not train you with this 20% of the features. We didn't train you with this. So this is a new ball game entirely. So we feed it to the model. Oh yeah, predict the Y. That is, predict the number of visitors that will come based on this information set as it is. From here to from the beginning of the data set to this place are your X variable. So we are having how many X now? Okay, J is 10, 11, 12. So we're having 12 features under X. Why this M column is your Y. The whole data set from beginning to the end, including your target, everything, is now divided into two. 80% of the data set is for training the model. 20% is for testing the model. So let me go back. Okay. So that 80% now is what we put into this line of code. Models fit X train, Y train. 80% of the whole table is what we put into this place. This fit model. 80% of the whole table. You can see that's why we're having X and Y inside here. It means the whole table. The table is divided into X and Y, and that X and Y, 80% of it is what we put into this model. Okay. So the model has been trained. Now, what is remaining? X test and Y test, right? So now, we're going to use this X test now. Let me go back to this data set. So let's say, I've screwed now. Let's say this is the remaining 20% of the data set. Every other one to the top have been used to train the model. Both the X and the Y, everything like this have been used to train the model. Everything has been used to train the model. So we have the bottom now, the remaining 20%. So now this is the remaining 20%. Now the remaining 20% of the data, the X test, the remaining 20% is this. Up to this column. That's the remaining 20% of X. Don't forget, this M column is your Y. That columns that are your X. Columns that are your X. So this highlighted part now is the 20% of X. So if we're going to be using this 20% now to predict, what is remaining in our data set that we have not used is this. So now, this other one now, this X test now, we're going to pack all this information and feed it to the model. What you are telling the model is, with all this information now that I've highlighted, that I'm feeding it, predict these values. That's what we are telling it to do. With all this information now for the X test, predict this information, your Y test. That is what the Y predict is doing. So take note. That predict now is trying to tell us if the model successfully uses this information to predict the Y, then with this information that we are feeding it now, this X test, it should be able to tell us the answer it's supposed to be getting should be 114, 69, 146, 93, and so on. If it successfully predicts it 100%, these are the answers it should be getting. This is where the accuracy score comes. Sorry, we are dealing with regression. That is where the mean square error and R2 score comes. It will not check. With this information we have fed it now, we say, okay, predict Y based on this information, predict Y. So for this row now, row 33, the answer should be 114. So we feed it this information of row 33, 0, 0, 0 as the X test. The answer for the Y predict should be 114. But the truth of the matter is that it can never get 114. You understand? It's not God. It's not 100% perfect. But at least the aim of a machine learning is to reduce the error as much as possible. So a model that has the highest score should predict closely. Now, if we feed it with this X, now we feed the model with this X, your Y predict can be 100 for linear regression. Your Y predict answer can be 100 for linear regression. Then for SVR, support vector regression, the answer can be 110. The answer can be 110 for SVR, but for linear regression, it can be 100. So when you do the accuracy score, that is R2 score and root mean square error score, like the metrics, if SVR, because I told you SVR, the answer will come as 110, while linear regression, maybe the answer is 100. If the score comes out, SVR R2 score should be higher than linear regression R2 score. Why? Because SVR is closer to the real original score than linear regression.